Okay, for question number 1, we want to show that fx equal to square root of x on limit 0 to infinity is uniformly continuous on limit 0 to infinity, but not satisfy the Lipschitz condition on limit 0 to infinity. So first of all, we show the definition. For all epsilon greater than 0, there exists delta greater than 0, such that square root of x minus square root of y less than epsilon whenever x minus y is less than delta. So we notice that limit 0 to infinity is equal to limit 0 to 2 union by limit 1 to infinity. So since we know that function is continuous on limit 0 to 2 and 0 to 2 is compact, it is uniformly continuous on limit 0 to 2. Next, we want to prove that the function is uniformly continuous on limits 1 to infinity. Then we show that suppose function f is equal to square root of x is uniformly continuous on limit 1 to infinity. Given that epsilon greater than 0, let delta equal to 2 epsilon and xy is element of 1 to infinity with x greater than y such that x minus y is less than delta. Just now we just let delta equal to 2 epsilon. Then we get x minus y less than 2 epsilon. Then we divide both sides by square root of x plus square root of y. Then we get x minus y over square root of x plus square root of y is less than 2 epsilon multiplied by 1 over square root of x plus square root of y. Since we just state that for all x and y is element in the limit 1 to infinity, we can assume that square root of x plus square root of y is greater than 2. Then 1 over square root of x plus square root of y is less than 1 over 2. In here, we can change 2 epsilon can multiply by 1 over 2, and we will get this function is less than epsilon. So from the definition, we show that fx equal to fy. Then we change it into square root of x minus square root of y. Then we can change this function into this function by multiply conjugate, which is multiply by square root of x plus square root of y over square root of x minus square root of y. And we will get as x minus y over square root of x plus square root of y is less than epsilon. So we can say that function f is uniformly continuous on limit 0 to 2 and 1 to infinity. Then f is uniformly continuous on limit 0 to infinity. So for Lipschitz condition, suppose function f equal to square root of x satisfy the Lipschitz condition on limit 0 to infinity. There exists L greater than 0 such that fx minus fy is less than or equal L multiplied by x minus y for all x and y is element in limit 0 to infinity. For L, when L greater than 0, we can imply that 1 plus L greater than 1 and 1 greater than 0. So obviously 1 over 1 plus L is greater than 0. Then we power both sides by 2. Then we get 1 over 1 plus L power of 2. And 1 over 1 plus L power of 2 is the element of limit 1 to infinity. Then next we let x equal to 1 over 1 plus L power of 2 and y equal to 0. And we change x and y in function 1. And we will get square root of 1 over 1 plus L to the power of 2 minus square root of 0 is less than or equal L multiplied by 1 over 1 plus L power of 2. Then we simplify, we will get 1 over 1 plus L is less than or equal L multiplied by 1 over 1 plus L to the power of 2. Then we will get 1 plus L less than or equal L. So we know that 1 plus L is obviously greater than 0. Then for all L greater than 0, we will get 1 plus L less than equal L, and we will get 1 is less than 0, which is a contradiction. So we can say f is not satisfy Lipschitz condition on limit 0 to infinity. So that's all for question number 1.
So next, we continue to the question 2, which is about the process. So the question is, let's M1 and row 1 and M2 and row 2 be two matrix space, and F, which is M to the approach M2. Suppose F is continuous and on the M1, and F is closed subset of M2. Prove that F negative 1 is closed subset of 2. So the answer is let X be the sequence of F negative 1 that converge to the point of A substitute of the M1. That's mean for any epsilon greater than 0, there exists n such that d1 and n d of ns and x for all the n. Since f is continuous, we know that for any of epsilon greater than 0, there's a z of delta greater than 0 such that d2, fs, and fy less than epsilon whenever d1 sy less than the delta. Suppose f is continuous on M, we have to show that every point of f negative 1 is an interior point of the f negative 1. So suppose M to subset of M1 and Fp subset of F. Since F is open, there is a C of the epsilon greater than 0 such that Y especially if dy Fp and Y less than less than epsilon. And since F is continuous at P, there exists delta greater than 0 such that d1 fs and fp less than epsilon. If that dx, x and p less than the delta. Thus, x in the f negative 1 as soon as dx, x and p less than delta. So for the conclusion, for the any sequence nx in f negative 1 that converge to the point of x in the M1, we have that x is in the f negative 1. Therefore, f negative 1 is closed. Okay, thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nartakia binti Zuhari. My metric number is 216930. So I will be presenting question number 3. Question number 3 states that let M1 row 1 and M2 row 2 be two matrix spaces and function f is from M1 to M2. Suppose inverse capital F is a closed subset of M1 and capital F is a closed subset of M2. So we need to prove that F is continuous on M1. Okay, firstly, let's recall that if a set is closed, if and only if its complement is open. So let U be the complement of capital F, and since capital F is closed, then U is an open set in M2. Okay. So to prove that F is continuous, we need to show that for every point in the pre-image of an open set, there exists an interior point of that pre-image. So suppose F inverse U is open in M2 for every open set U in M2. So we fix P in M1 and epsilon is greater than 0. Then define the set U be the set of all Y in M2 such that dm2 y fp is smaller than epsilon. This set U is open in M2. Therefore, inverse function of U is open in M1. This implies that there exists a delta greater than 0 such that it contains all point x in inverse function of U. As soon as dm1 px is smaller than delta. But if x is in F, if x is the element inverse of U, then function fx is in U. So that dm2 fx fd is smaller than epsilon. So by definition, f is continuous on M1. So that's all from me. Thank you for your attention.
Hello, Prof. My name is Lim, and today I want to present question 4 for our SCL. So for question 4, here is a statement we want to prove. If A is a closed subset of a compact metric space M, then the metric space A is also compact. Okay. So here we take note of two conditions. The condition is this subset is closed. The second condition is the big space or the ambient space M is compact. Okay. And then we want to prove the subset A is also a compact metric space. Okay, here we start the proof. So suppose the condition M is compact, and then A is a closed subset. Okay, now because any subset will be also a metric space, any subset of a metric space is also a metric space. So this one, A is already a metric space. Okay, so what we have to prove is A is compact. To show A is compact, we have to show by definition this statement, which is for every open cover of A. So this open cover can be it's a union. It's a union of open set. Okay. As shown in here, later I will show. And there exists a finite open subcover of A. So what's the meaning? Meaning is that so first we let this one is a collection of open set. V alpha is open. Okay, V alpha is open as shown here. V alpha is open for all the alpha in the family F. So here the F can be any set, can be finite, can be infinite. Okay, so F can be anything. So we don't know yet whether it is infinite or finite. Okay, so we just say a family. Okay, by means of open cover, we means that the A is a subset of the union of all the open set, of all the open. So we say this is an open cover of A. Now, of course that any collection, any union collection of open set is still open. So this is called the open cover. Okay, this union can be a finite collection or can be an infinite collection or can be uncountable infinite collection. Okay, now we set a new set called OM, okay, OM, to be the union of this open cover with A complement. So A complement is not in A, okay, the set that's not in A. Okay, now we take note of a very important thing, which is if A is closed, then its complement is open. This is true for all set. Okay, A is open, mean if and only if A complement is closed. So this is a two-way statement. Okay, now so this is a union again, union of open set and open set. So this one also is open. Okay, now furthermore, this is also an open cover of M. Okay, to see why it is an open cover of M, we can draw a simple diagram. Okay, we can draw a simple diagram. So this big set is M. Okay, this big set is an M metric space. So we have a subset called A. Now, just now we say that there's a open cover. So let's say this is the open cover, because open cover means the union of everything. So let's say this is the union of all the open set, okay, to cover A. So these all are V alpha. Can be infinite, so let's just call dot dot dot. Okay, now A complement is all outside of A. So can I color it as like this? So this all, including outside, is the A complement. It's the A complement. So now to see why it to see why this one can cover M, because A complement is all outside of A. Okay, and then some more, the purple color one, which is the open cover, can cover A. So their union can be everything inside the M. So that's why that this set is a open cover of M. Okay, so because we said at earlier that M is the ambient space or the big space. So if something contain M, means that actually they are the same. Means that the OM is actually our M. Okay, so this is an open cover. Now, we have to use the second important assumption that M is compact. So because M is compact, so by the definition, it has a finite subcollection, the new set of the original set, this one, such that this new set is also a subcover of M. Okay, in other words, writing symbolically, we means that the subset phi, okay, where phi is finite and then phi can cover M. Okay, so by means of finite, we means that there is the finite means there is a bijection to some finite natural number. So let's call N. So we can restrict our F, maybe it's an infinite set, to a finite set, which we denote all the alpha to be some specific alpha 1, alpha 2, up to alpha n. So this set is a finite with n elements. Okay. And because this set can cover M, so we can writing them down. So this infinite set become a finite set, of course, union with A complement. Okay, we do not know that whether A complement can contribute to cover M or not. So we have to include this one also. This one have n element. This one is just one element only. So the union of this one consists of n plus one element, which is also finite. So this is a finite subset of the OM. Okay, now, because A is a subset of M, A is also a subset of M, so we can write A subset M, where M is also a subset of this new set. Okay, so by transitive property of the subset operator, so this one is a subset of this one. A is a subset of the finite subcover. Okay. Okay, I mean the finite open cover. Okay, here we cannot say subcover yet. Here is the reason. Okay, we cannot set it. We cannot say that the phi is a subset of this one. The reason being is because the A complement. The A complement is an extra thing. So now we can remove the A complement from the phi. The reason why we can remove A complement from the phi is because that A complement and A have no common element, which means that A complement actually cannot cover A. It contribute nothing to cover the A because they didn't have any element lies in A. Their intersection is a null set. Okay, so now so A can contribute nothing to the effect of covering A. Okay, here, so now we can define a new set by removing the A complement, which is just left with the finite union of the V alpha. So here we use alpha I to denote all the alpha 1, alpha 2 up to alpha n. Okay, now this 5' is already a subset of the original open cover, okay? Because here we use a subscript alpha I up to alpha n, and this one alpha can be anything from the F family, okay? So now we have already proved what we want to prove, which is for every open cover, this one we specify of a closed subset of A, there exists a finite open subcollection, this one, okay, which is also an open cover or open subcover of A. So which by definition, A is compact. And here we have done the proof. Thank you.
Hi, my name is Sarvin Analaki Wadivilan and my matrix number is 216886. Today I'm going to explain the question 5. Suppose f is a bounded function defined on the closed bounded interval AB. If f is Riemann integrable on AB, prove that for every epsilon more than 0, there exists at least one partition P such that the upper sum of f minus the lower sum of f with respect to partition P is less than epsilon. Okay. Since f is Riemann integrable, the upper and lower sum converges to the same value, which is the limit of partition P towards 0 for the upper sum is equal to the limit of P towards 0 for the lower sum is equal to the integration from A to B, which is the bounded interval. For any epsilon more than 0, by definition of Riemann integrability, there exists a partition F such that the upper sum with respect to partition P minus the integration from A to B is less than epsilon over 2. The same thing for the lower sum. The lower sum of F minus the partition P, the lower sum of F with respect to partition P minus the integration of from A to B is less than epsilon over 2. So by using triangle inequality, the upper sum minus the lower sum is less than or equal to, we just substitute the value down. And then we will get less than epsilon over 2 plus epsilon over 2, which is epsilon. So therefore, there exists a partition F such that the upper sum of F minus the lower sum of F with respect to partition P is less than epsilon. Thank you.